Hi again. Well, here we are with the ideal gas law, PV equals nRT, or PERVNERT. This is the gas law that you use when you're changing more than just two variables at a time. But first, before we get into that, I searched the house for a balloon, couldn't find one, but I do have a rubber glove. So what is the pressure inside this sort of balloon at this point in time? Okay. It's equal to the pressure out here. Okay, there's 1 atm roughly of pressure in here. Now, what if I got the balloon really, really cold? What would it do? Okay. According to Charles's law, as the temperature decreased, the volume would also decrease, so the balloon would shrink. If I heated it up, then the opposite would happen. It would inflate, and probably until this really lousy knot I tied slipped open, and then it would deflate. But all right, so there's the basics. Okay, when pressure goes up, volume goes down. When temperature goes up, volume goes up. And then we don't have a law that directly relates pressure to temperature, but we can probably reason it out. If you heat up a gas, then the molecules travel faster. And the faster they're traveling, the more often they're going to run into the walls of the container. And those collisions with the walls of the container cause the pressure to go up. So temperature and pressure are also directly proportional. When T goes up, P goes up. So you could use your little PVT card thing I gave you to verify that if you don't believe me. All right, let's dive into the ideal gas law. Now, you know that P is pressure and V is volume and N is moles and T is temperature. What the heck's R? Well, R is just a proportionality constant that makes the equation work out. So it's sort of like pi, it's just a constant. The thing is, R has different values depending on what units you're using for pressure and temperature and volume and such. So, well, of course, for gas laws, the temperature is going to be Kelvin, but pressure can be in ATMs, it can be in pascals, it can be in torr. I remember using the second one quite a bit in physics. Okay, same with that one. But what are we going to use in here? Generally, we're dealing with our gases and volumes of liters, pressures in ATMs, moles for our amount, of course, and Kelvin for our temperature. So as long as you use those units, you can use 0.08206 for your value of R. I never really mess with the other ones very often at all. So commit that one to memory, save you some trouble in the future. Okay, say that again. As long as our pressure is in ATM and our volume is in liters and our temperature, of course, always has to be in Kelvin, then R is equal to 0.08206. All right, so here we are. The ideal gas equation is awesome because it relates all four variables. The thing is there's no such thing as an ideal gas, okay? An ideal gas is a hypothetical gas that doesn't even exist. The good news is at low pressures, most gases will behave ideally. Okay, so most gases, if you take their pressure times their volume, that'll equal their moles times R times their temperature in Kelvin. Especially at low pressures, it tends to work a lot better. And we'll talk about why it works better at certain conditions than others a little later on. So as we already said, there's other values for R, but I'm always going to use this one. Okay, now most gases behave ideally. So this is the molar volume of a gas. Remember, a mole of any gas at STP should be 22.4 liters. And most of them follow that fairly closely. This one down here that you can't see is hydrogen. That's 22.42 instead of 22.41. Hydrogen and helium are very close. So is the nitrogen. Probably the biggest deviation is the chlorine. I will get into why that is a little later on, why some gases deviate more than others. Just for right now, trust me that they do behave ideally. So remember, STP means standard temperature and pressure. That does not mean room temperature and pressure because it's flipping cold. Okay, standard temperature is 0 Celsius or 273.15 Kelvin, and pressure is 1 atm. All right, so the molar volume of a gas at STP, no matter what the gas is 22.41. Once again, I usually use just 22.4 because we're generally only going to have 3 sig figs in our calculations. All right, so at standard temperature and pressure, so at STP, how many moles of gas are present in a box with a volume of 112 liters? Okay, well, we know a mole of any gas takes up a volume of 22.4 liters. So how many moles are in there if it's that many times greater? If it's 112 liters instead of 22. Okay, I set it up as a conversion factor here, and you've seen this before in Chem 1. Only bust out the 22.4 when you're talking about gases, and only when they are at standard temperature and pressure. A lot of us have been trying to use this already when we were talking about solutions, but no, this is a gas constant here. So we have liters, we want to get to moles, we put the 22.4 liters on bottom, 1 mole on top, 5 is our answer. Or if you really wanted to do a lot of extra work, you could plug in a pressure of 1, a volume of 112, solve for N, and plug in a temperature of 273 for the Kelvin. Do the algebra, solve for N. You'll get 5 that way too. I like the conversion factor way. Just remember, you can only do this 22.4 shortcut if the gas is at STP, standard temperature and pressure. All right, this one is not at STP, so we're going to have to do use PV equals nRT, and we are looking at how many moles of CO2 were generated. Okay, I thought this was going to be more complicated than it is, but it's not. So this is not at STP because we're at 31 degrees and 1.3 atms of pressure. So got to take our temperature and convert it to Kelvin, add that 273. Our pressure is already fine. Our volume does have to be in liters, so just scoot the decimal over. Now we can plug it into PV equals nRT and then solve for N, and that's our moles of CO2. Ta-da! So just algebra. Now, this is probably my favorite gas law right here, the combined gas law. What that's based on, it's sort of like the dilution formula, M1V1 equals M2V2. It's similar to that because it's using the similar premise. If you have a container of gas and it's a sealed container, constant number of moles, okay, and you go changing the pressure and the volume and you want to know what that's going to do to the temperature, you can set PervNert equal to itself because you know, since it's a sealed container of gas, that you've got the same amount of moles. If it's a sealed container, same amount of moles, you've just changed T and P. Instead of doing PV equals nRT twice, I'll have to show you what I mean by that. Instead of doing a lengthy calculation, you can just cheat and jump to this guy, the combined gas law. So it is what it says it is. It is the combination of all the gas laws. So we know pressure and volume are inversely proportional. We got that from Boyle. Then Charles taught us that temperature and volume are directly proportional. Then we got Gay-Lussac, which brings up the pressure and temperature relationship. When temperature goes up, pressure goes up. And then, of course, Avogadro's law that when moles go up, volume goes up. Okay, if you put that all together, you get P1 times V1 over T1 equals, and sorry if you can't see it all right now, but the same thing, just with 2's. Pressure 2 times volume 2 divided by temperature 2. So if you have a isolated sample of gas and you change 2 variables and you want to predict what it's going to be like after that in terms of a third variable, you can use the combined gas law. So we often have situations like that where pressure, volume, temperature are all changing, but the moles are the same. It's a sealed container of gas. So we can use this equation. The moles have to stay the same though. Okay, so here's an example of one like that. Inflating a balloon that has a volume of 6 liters at sea level, which is 1 atm of pressure. And then it's allowed to ascend in altitude until the pressure drops to less than half that. But also during that ascent, the temperature is going to fall. Calculate the volume of the balloon at its final altitude. I like this question because you have kind of two conflicting changes happening here. The pressure drops, and we know pressure and volume are inversely proportional. So when the pressure drops, our volume is going to increase and our balloon is going to expand. But it's going to get colder too, which will cause the balloon to shrink. So which one's going to win out? Okay, so we're trying to figure out what the final volume is going to be at the balloon's final altitude. Will it have expanded or contracted? So they set up a little chart here of our initial pressure, volume, and temperature. We know the final volume and temperature. That's pressure, not volume. Sorry. We know the final pressure and temperature. I think I might have said volume. We're looking for the final volume, though. So this is a perfect situation for the combined gas law because the balloon is sealed and contains a certain number of moles of gases. That's not going to change, so we can just use the combined gas law. They rearranged it algebraically before they put the numbers in. Your textbook does that. I don't know. I'm just lazy. I like to write the formula the same way and just plug in my numbers, and then I just make my calculator do all the algebra. So when it's all said and done, the final volume is going to be 11 liters. So the volume increased, it expanded because the pressure decreased, so our volume increased. The temperature change wasn't significant enough. It was only, a couple degrees, so the temperature change wasn't enough to make the balloon shrink in volume. It just didn't grow as much as it would have. All right, here's another one. We have a gas at a pressure of 1.5 atm. The temperature is 25. That is about room temperature. Assuming that the gas obeys the ideal gas equation, PERV-NERT, what would the pressure be if the can was heated to 450? Okay, what law do we need here? We've got a P and a T, and then we've got a new T. And we're just trying to figure out P. Okay, we could make this complicated, or we could use that Guy-Lussac's law. Pressure and temperature are directly proportional, so P1 over T1 equals P2 over T2 would work perfectly here. We just have to remember to convert to Kelvin first. Okay, so voila, and so our final pressure would be 3.6. All right, and then we can also see if our answer makes sense. Okay, we got it hotter, so it would make sense that the pressure would increase. Okay, the molecules are moving faster because they're hotter and they're colliding with the walls of the container more, and so that's more pressure. That's why it says on hairspray and spray paint bottles and stuff, do not incinerate. Don't throw them in your burn pile. It's not safe to burn trash anyway, but definitely don't throw those in there because they can explode and projectile, hurt people, etc. All right, further applications of the ideal gas equation. With a little bit of algebra that I won't bore you with, you can take PERV-NERT and rearrange it and get it to include density. Okay, and so if we know the density, the temperature, and the pressure of the gas, we can go so far as to figuring out the molar mass of the gas, which can then lead us to the identity of the gas, as we've already done before for molar mass. So I call this the dirt P equation. Molar mass equals dRT over P, where big M is the molar mass. I usually write 2M so it doesn't get mixed up with molarity. And D is density, R is the same old R, T has to be in Kelvin, and pressure has to be in ATM. Now remember, density is mass divided by volume. Okay, so I'm almost out of time. Well, shucks. Okay, wait for the next video then.